Okay, welcome back to Feedback Control Systems. This is Module 10.1, Feedback Compensation. The objectives of this module is to provide an introduction to feedback compensation. For the most part, we've been doing unity gain feedback, and so we're going to look at an alternative way to do compensation with feedback. So first, we're going to have our first approach, which is called rate feedback. Then we're going to look at an example of rate feedback. Then a second approach is going to be what we're going to call minor loop feedback. Then we're going to work an example of that as well. So first, as an introduction, so feedback compensation is an alternative to what we've been doing so far, which is called cascade compensation. So putting the controller in series with the plant. So the design procedure can be a little bit more difficult with feedback compensation, but the benefits are it can result in a faster response and potentially can handle some noise problems a little bit better. So what I'm showing you here is two loops, a major loop which has unity feedback, which essentially can take back the desired output, and then maybe a minor loop here taking an intermediate term as shown right here. So this is what we mean in terms of some feedback compensation is, whether we look at this minor loop, etc. Now, an example of showing you the minor loop right here is we could think of like a tachometer. So we might have position, and to get to velocity here, we might want to have a tachometer that can distinguish, okay, I'm measuring some position and then outputting some velocity signal as shown here. And so that might be a type of system that we have for this tachometer, and then maybe feedback that sort of as an intermediate term. So we can feedback position here and then feedback the velocity term there, and then look at that as part of our an alternative for feedback compensator. Okay, so that first thing we're going to look at is a rate feedback. So here's the same block diagram. Now, I'm not going to walk through the steps, but in earlier modules we showed you how to do a block diagram manipulation. And so what I'm saying is we can take this system right here and make it look like this. So relative, our RS, CS on either ends, as shown here, they're the same. And then so I'll leave it to you as an exercise to see if you can get from this left diagram to this right equivalent block diagram. And there's a big hint if you have the book. They walk you through that step in the book. But I'd say try to see if you can get from here to here by yourself, and then use the book as a check because they give you a little bit more hints in terms of how to walk through that. But I think that'd be a great exercise for you to try. So we have this equivalent block diagram. And if we look at the loop gain of that, you'll see the loop gain here, our GS term here, and you'll see it as written there. It's has common parts here, K1 and G1, really, which you could think of as right in the center. And then I have this feedback term, and then this sort of G2K feedback term as well, those sort of added, and then that combined multiplied with the sort of plant K1, G1 term. So that would be the loop gain. Now, if we didn't have this feedback term right there, the loop gain would essentially do what? It'd get rid of that, and then I'd be left with just this term right there. So we can kind of do that compare and contrast. What benefits could I have with or without that sort of minor loop feedback? So adding the feedback, what does it do? It replaces the poles and zeros of G2 with the poles and zeros of this intermediate term here. So this intermediate term is what we saw right there. Okay, so we have a little bit more flexibility, design flexibility as is shown there. So the zeros of the equivalent feedback are not going to be the closed loop zeros. So looking at our equivalent block diagram, right, and this feedback path that I showed here, that's what I'm going to have there. So the zeros of the equivalent feedback are not going to be the closed loop zeros. That's going to be very important as we go through and look at this approach. Now, if we make our G2 right here, if we make this equal to 1, and if we say our KFHC feedback is a rate sensor, so for example KF over S, we could change our loop gain and make those substitutions in here. Let's just clean up some ink. Okay, so again, if I look at this system with G2 right here equal to 1, Okay, and if this term right here turns out to be a kf over s term right there, then we can basically substitute and come up with a total loop gain as shown right there. And with a little bit of manipulation, we can see we have a 0 at minus k over kf. Okay, so I have a 0 relative to this k and kf term right there. Okay, so that will be sort of a thought process. Now we're going to dive into an actual example and kind of work through and see what we can do here. So I want to design a rate feedback compensator to reduce the settling time by a factor of 4, and I want to maintain an overshoot of 20%. So here's our system. Notice we have 3 poles, no zeros in our uncompensated system. Okay, we have a pole at 0, -5, and -15. You can see them right here. 0, -5, -15, and we don't have any zeros. So our uncompensated root locus and step response shown below here. So again, we've walked you through enough of these processes here so we can vary our gain k so that we are on this 20% overshoot line. So the poles at 0 and -5, as we vary k, come together, go off axis, and again, where do they intersect that damping line to get 20% overshoot, and we're going to get a K, as you can see here, of about 257.8. Then if we were to do a step response right there, here's what CS, this would be our output here. And you'll see that we have a settling time of just about 2.21 seconds. Okay. And then, you could find out what the overshoot is, the TP terms, any other transient goals that you want. Okay, so now that's our uncompensated system. So we now want to look at a rate feedback compensator to reduce that settling time by a factor of 4. So we know that we can take the 2.2 divided by 4. We get a desired settling time of just over a half a second. Okay, we can then take that, just like we did in previous modules, and find on the real axis the sigma term, which is negative zeta omega n, and then the j omega axis term, omega d, right here. So that sigma omega d, we could find those terms based on, here in green, given our uncompensated system as shown there for that gain, we can actually design our sigma and omega d terms as shown right there. Okay. Then the next step in our process was to look at all the uncompensated poles and zeros. Well, there's just poles. We have the 3 poles, no zeros, and then the compensated pole. And then what we find is we have negative 277. We know by now that that has to sum up to an odd multiple of 180 degrees. And so what we find is we're going to need a compensator 0. Okay, to contribute based on that 97 degrees. That's that angle that we have there. And then so as we design that compensator 0 here, we can find it to be at about 5.42, just to the left of the value right here, our sigma value for our dominant pole. Okay, so we have our compensator 0. And again, I'm going through that a little bit quick. We had seen how to do this in a previous module, so I don't want to spend too much time on that. Hopefully you can follow, and if not, please, by all means, ask questions. And then so once we have our compensator 0, and you'll see that right there, compensator 0 right there. What we can now do is vary our root locus and see where we get on that damping line to give us that 20% overshoot, and we get a K, in this case, of about 1388. Okay? So now we're going to look at our rate feedback compensator, and here's the example that we can do for this example. So given our system that we had here, okay, what we can do is draw an equivalent block diagram for our system as shown right here, and we get this equivalent block diagram as shown here. Now notice one thing I did here for this this kf of s, when I combined it with this term right here, again I get this equivalent block diagram, and notice this kfs plus 1 over kf, essentially these are going to be equivalent to each other, okay? So then I can take the feedback term, combine it as we had done previous modules where we did have an H of S in the feedback path and make that look like a unity feedback system. And that's what we're showing there. So you can see K1 and KF embedded into that main transfer function. So K1 of 1388 was from our compensated root locus. Okay, so let's just go right here. Here's our K1. Our 1388 was from our compensated root locus that we saw on the previous slide. Now, KF is going to be the reciprocal of the compensated 0. So we found the compensated 0 on the previous slide as 5.42. So the reciprocal of that will give us our KF. And then what we can do is, with our KF known, we can look at our our steady state error characteristic right here, looking at our static error constant right there. And then given that KF and a value of K1 that we know, we can solve for our KV, and in this case gives us a value of 4.18. Okay. Next, what we can do is generate our closed loop transfer characteristic as shown here. And so I have my GS over 1 plus GS HS term, and then I can get my closed loop characteristic from this block diagram. And then once I take the values that I have of my K1, my KF terms, everything that I have right here, I can simulate, find where the pole locations are here in the denominator, and then get my step response. Now, when I look at the step response, it looks pretty good. There's no overshoot. It's pretty quick, and I can put a table together showing first my uncompensated system, compare it to the compensated system. So in terms of overshoot, I get 20% in both cases. And then my settling time, again, our goal was to reduce it by a factor of 4. So here was the original, here's by a factor of 4. Now, wait a minute. I thought my desired overshoot when I did this root locus design 20%, but I would expect something like that, but I don't get it. It looks more like it's critically damped. So again, when I look at my dominant poles here for my uncompensated system, we can see they are complex conjugates, so we would expect overshoot here. And then for the compensated system, I have those poles here as well. So why does this closed loop character, did I get the wrong plot here, or what's going on? Well, this is a step response, and then but when I would look at the error relative to our like a ramp input, you'll see that it's actually kind of similar. So what I'm saying here is you can actually get a better response, and you could say, well, does this really meet spec? Because I'm expecting 20%, I'm not seeing anything. But in terms of settling time, you know, things look quite well. So again, I'll leave that for you to decide which is better, which is not. But we are kind of showing you an approach of what rate feedback can do for you, and see if this is something of interest. Now, what I would like to do is look at what we're going to call our minor loop feedback. Here's our goal. We want to design our minor loop with a damping of 0.8 and a closed loop damping of 0.6. So the minor loop damping, so again, this is the minor loop, we want that to have a much higher damping than the sort of closed loop full response. So we're going to walk through this and see how we can do this. Okay, so our minor loop transfer characteristic is going to be as shown here. So you can see, based on this minor loop, see if you can solve for that characteristic, that very simple, I think, transfer function to get. I'll leave that for you. Now, the open loop transfer function of that minor loop is just that product. Okay, so I just have KF S in the top, and then this is in the denominator. So the open loop transfer function is just the two blocks multiplied by each other, but the total transfer function, again, forward path, and then looking at loop gains and stuff like that. So I'll leave that again for you. But the open loop, again, should be pretty straightforward. The minor loop, a little bit of algebra, but I think you should be able to get that final form as shown there. Now we can do the minor loop root locus as shown here. And when we look at this, notice the following. We have a pole and a 0, both at 0 here. So those essentially look to cancel relative to the open loop characteristic. And then we have the two open loop poles here, one at -5, one at -15. Okay? So I need to make a comment here. So the 0 that's at the origin is from the minor loop, and that's what we see here from our open loop transfer characteristic. And as a reminder, this is not a closed loop 0, so this will not cancel the pole that's at the origin. Even though it kind of looks like there's going to be a cancellation, this is one of those kind of gotchas that you have to watch out for when you're doing this minor loop feedback, is really a minor loop 0 and not a closed loop 0. So more of that as we move forward, but I just wanted to make that reminder as I have it right here. Okay, so now, if I look at the real part of the complex poles, they're going to be constant at this location -10, and that's what we see here, because relative to that root locus, look what happens with the root locus. I have the terms, one at -5, one at -15. As I increase gain, they come together at roughly -10, and then they go off axis in a vertical formation. So the point here is that this will always be at -10. And so the damping ratio now will have to vary because remember, in my general characteristic equation, so this is our general characteristic equation, omega n squared over s squared plus 2 zeta omega n times s plus omega n squared. Okay, so I'm really looking at this point right here, 2 zeta omega n, and that's what I'm showing here, 2 zeta omega n equals 20, which is a constant. Okay, so what I'm saying here, since that's a constant, what's going to happen is the damping ratio will need to vary to keep that term constant here. So as I'm looking at that, here initially I have a damping ratio of 0.8 because that's where I want to design my minor loop. Okay, and for that location, if I get a KF of 81.25 as shown there, you'll see where the pole locations are, -10 plus or minus J 7.5. Okay, so I've achieved my minor loop damping of 0.8. Select that KF term to give me what I want. Okay. Now the minor loop poles, as shown here, the minor loop poles at s equals 0, that's right. That's that pole of 0 there, right there, and then -10, and then plus or minus J 7.5. Okay. So let's restate that. The minor loop poles are at s of 0, and the poles that we found by varying KF, and they are now the open loop poles that are going to be used to vary K, this K, because I've already designed my minor loop here, so I've fixed my KF. Now I'm going to use that to vary my K to find a closed loop system with a damping of 0.6. Okay, so that's what I have on this slide right here. So now my open loop poles are going to be 0, and then what were my minor loop poles based on my KF selection. Okay, so now what do I need to do? I need to now vary my K. That K is part of that compensator in that forward path, and as I vary K, look what's happening now. the poles go in this direction. Now I want to see where they intersect with my damping line of 0.6. So I vary my K, and you'll see I get a K of about 624 as shown right there. Now I got to be careful with that K because those poles will kind of come in, and then if I keep increasing them, look where they're heading. They're heading off into the right half plane, which would make the system unstable. Okay, so the step response for that value of K takes on this form right here. Okay, and then what we could do is do that comparison of the uncompensated system versus the compensated system, where the percent overshoot is roughly the same for both, and the settling time has come down by more than a factor of 2. So again, we wanted the minor loop with damping of 0.8 and the closed loop with a damping of 0.6. Okay, and we would have expected different overshoots. However, we ended up with the same overshoot as shown here, but we did get an improved settling time, improved peak time as well, and we also achieved a little bit better result relative to a ramp input in terms of a steady state error associated with that. Okay, so this will conclude our module on feedback compensation. We looked at rate feedback, minor loop examples, etc. as, again, alternatives to just having unity gain feedback. And what we saw is you can, in the two examples, maybe really get overshoot that is less. What we found is it's even better than what's simulated. Again, these were sort of theoretical predicted, and it may be better. And so what we'll see here is that design gets a little bit more tricky in terms of here's what we're designing, here's what we see in simulation, but overall it looks like an alternative way to design our systems. So if you have any questions on any of this material, please don't hesitate to reach out. Thank you.